Welcome to students. Initiated the study of subshift of finite type. Basically, subshift of finite type are those shifts for which the forbidden blocks can be represented finitely. And today we shall again continue with the same thing, but let me recall a few things that we may need, which we did last time. So, first of all, I start with the definition of subshift of finite type. So, subshift of finite type is basically a shift space for which the forbidden blocks, right, the representation of forbidden blocks is finite. And we had again seen something else over here, and we had seen that. So, we have a graph G, V is the set of vertices and E is the set of edges. Then for this graph G, with adjacency matrix A, we can define a shift which we can call it as xg or xa to be the set of all xi So, basically this is a subset of the set of edges to the power z such that your terminal part of xi is equal to the initial part of xi plus 1. The initial vertex and the terminal vertex of xi is same as the initial vertex of xi plus 1. So, all such factors, right, all such sequences is something which gives us, so this is a bi-infinite walk on the graph G, and that gives us something called the vertex shift. And we had seen that every vertex shift is a subshift of finite type, and also that every subshift of finite type cannot be represented as a vertex shift. So, we had considered this example that you take x equal to xf with f being just the block of 1 1, then we could not represent this in terms of a vertex shift. But then we are interested in representing every subshift of finite type. Supposing we are interested in representing every subshift of finite type as a vertex shift. So, what can be done for this such particular cases? So, all we can say here is that our subshift of finite type, again this is something again which we are recalling again, that every subshift of finite type is an m-step subshift of finite type, right. There is some m for which it is an m-step subshift of finite type, and for this subshift of finite type, what we have here is that you consider Bm plus 1 of x, which is basically the set of all admissible blocks of x, and then all admissible blocks here, and then you think of that part that okay fine, look into this as your edge shift. So, give this to be, let this be the set of edges, and then we can always find another graph G. So, let me call it G prime with some set of vertices and the set of edges as E prime, such that your xf can be written in terms of x G prime. Now, we shall try to see how this can be done. This is basically done using the higher block representation. Let us take the case of the same example here. So, again we have our subshift of finite type, we have x equal to xf with f being the block 1 1. Now, what happens in this case is we can think of again two vertices here. Our edge 0 0 goes here. Now, this is a higher block representation. So, one has to be very careful, since we have a 0 here, the next part here should start with a 0. So, we have a 0 1 here, and again since we have a 1 here, the part here should start with 1. So, we have a 1 0 here. So, now this is an admissible graph, right, and one can see that this graph, this edge shift, right, with my edges being now 0 0, 0 1 and 1 0, with these edges this gives me a edge shift, right, this gives me an edge shift, and that edge shift is basically my this golden mean subshift of finite type. So, what we get here is that supposing now my G prime happens to be V E prime, then x G prime is same as x f, which is basically the golden mean shift. So, one has to get into a higher block version to convert a subshift of finite type into a edge shift, and hence we can say that every subshift of finite type can now be represented as an edge shift, right, but what are the alphabets there, right, it depends on whether you can directly write it, right, or you could need to take the higher block version and then write it, right. So, this is one case. The other thing, alternately way of looking into subshift of finite type is that, so alternately take a matrix B. So, let me specify that B is a k cross k matrix. So, take a matrix B of zeros and ones. So, the only entries of B are zeros and ones, and now let this B be an adjacency matrix for some graph G. So, let B so, we can think of this graph G will have, so this graph G will have k vertices. So, now we can think of that this gives us the vertex shift which we can call it as x g or we can call it as x b given over the k symbols. So, we can think of the k symbols as 0, 1 because k minus 1 over the k symbols defined as, this gives defined as so, we have this x g, this is equal to x b. This is basically again I am looking into x I going I in z such that my b of x I plus 1, this is 1. If it is 1, I can define the sequence, this is permissible for every I belonging to z, and my x i's basically belong to this vertex V. So, vertex V of G, where I can think of G as the set of vertices here. So, G is V E. So, my V happens to be this particular set 0 1 up to k minus 1. So, we think of this vertices and we say that there is an edge between two vertex if you have b x I plus 1 to be equal to 1. So, in that case we say that this vertex becomes, so x I is the vertex. Say for example, we can think of our b to be equal to, again we take this matrix 1 1 1 0, and for this we can easily define the vertex shift. So, now since I have this 2 cross 2 matrix, I have two vertices, I can label them as 0 and 1. And then I want to see that between 0 and 1, between 0 and 0 is there an edge. So, this is 1. So, between 0 and 0 there is an edge here, between 0 and 1 also there is an edge here, between 1 and 0, there is again an edge here, but there is no edge between 1 to itself, right, because this is 0, and hence one can think of that we get here your x b, right, and if you look into this edge shift, this is basically your golden mean shift. So, we get the golden mean shift here, looking into it as a vertex shift. So, you can either represent a subshift of finite type, you can represent a subshift of finite type as a vertex shift, or you can represent a subshift of finite type as an edge shift. So, you have edge shift and you have vertex shift, you have both the cases here. Now, we see that this vertex, this is a subshift of finite type. So, our vertex shift is a subshift of finite type. Where you are looking into the forbidden blocks, right. So, with the forbidden blocks, all I j, right, such that b I j is equal to 0. So, finitely many of them. So, this is always going to be a subshift of finite type. How do we look into an m step subshift? So, this was just a one step subshift of finite type. How do we look into an m step subshift of finite type? How do we represent that in terms of a vertex shift? So, we note here that every m step subshift of finite type can be written as a vertex shift by taking the higher block representation as alphabets. So, what you have here is that supposing now if I look into a block, right. So, this subshift of every subshift of finite type will be m step. So, supposing I am looking into this block A1, A2, A3, A4, A5, right, AM plus 1, AM plus 2 and so on. Then we know that this A to the A up to A plus AM plus 1, this is permissible. So, we start with a vertex here. So, I call this vertex as A1, A2 up to AM plus 1. I take another vertex here A2, A3, AM plus 2, and then I can take a third vertex here A3, A4. So, I am looking into all m plus 1 blocks here. So, this is one vertex, this is another vertex and this is a third vertex. Now, when we are constructing a graph, since this is a higher block representation, we see that this part should coincide with this part, and if this part coincides with this part, right, then what you have here is you have an edge here. Now, since this part does not coincide with this part, right, we cannot have an edge from this vertex to this vertex. And then when you are looking into this part, right, so you say that okay fine, from here this part, basically this part, the last part, terminal part here coincides with the initial part here, and hence there is an edge from this to this factor. So, you are drawing in a vertex shift in this particular manner. Now, you could also think of this as an edge shift. How do you think of this as an edge shift? So, supposing I have taken these as my vertices, then you say that you want to draw edges and your edges should be labeled also. So, what you try to draw here is you say that okay fine, between this and this, so this becomes this combined with am plus 2 happens to be a permissible block. So, you draw a shift here, you draw an edge here and you call this edge as am plus 2. So, you have this factor am plus 2 takes you to this particular factor. So, then you are removing the first part, you are just retaining the last m plus 1. So, last m plus 1, so this brings you here. Then this again is permissible. So, this is like this block coincides with this block. So, again there can be an edge from here to here and you take an edge from here to here and you call it as a, this was m plus 2, this is a m plus 3 and you can have an edge from here to here. So, the higher blocks definitely help us in converting subshift of finite type or converting a graph out of subshift of finite type, and henceforth we can say that whenever we consider any subshift of finite type, right, we equivalently have a graph representing it, whether we consider it as a vertex shift or we consider it as an edge shift, there is a graph representing it, and whenever we have a graph, we know that there is an adjacency matrix associated with the graph. So, every graph has an adjacency matrix and so there is a matrix basically which is responsible or which characterizes every subshift of finite type. So, for us a subshift of finite type is same as a matrix, and now if you want to code it up, right, it is very easy, you are just using a matrix to code a subshift of finite type. So, the entire dynamics can be just coded using a matrix. Now, what is more important here is to see what is this characterization, what is this relationship that whatever it was, what is this information that we can get from the matrix which can help us deduce some kind of results or some kind of properties, dynamical properties of a subshift of finite type. So, I would just like to recall some definitions of a matrix. So, we start with this factor, we look into some definition here. So, a matrix, say let me take again a k cross k matrix, is called irreducible if for every pair, so I am starting with I and j less than or equal to k, there exists an n, right, some n which is positive, right, some natural number such that I take a to the power n and then take what is its ijth entry. So, this would be positive. So, we say that a matrix is irreducible if whenever you have any pair I and j, so you are looking into any combination I and j between 1 and k, then there would be some n such that a I j k, if you are looking into a to the power n, then this its ijth entry is positive. So, that is what is called an irreducible matrix. And again we have something more about a matrix. So, we say that a matrix is called aperiodic if, again what we have here is, we have now something different from here, if there exists an n positive such that a n I j is positive, right, for every between 1 and k. So, for every I j between 1 and k, if your a n I j is positive, then we say that this matrix is aperiodic. The only difference between the two comes out to be that for this particular n, it is quite possible that some I prime j prime, right, the I prime j prime entry could be 0, but for here whenever we take a n, right, all entries are strictly positive. So, that is basically what we call as an aperiodic matrix. And now we have a theorem Now, the theorem says that a subshift of finite type now we know that a subshift of finite type can be described in terms of a matrix. So, subshift of finite type is transitive if and only if this matrix A is irreducible. And if we want to look into the proof of this theorem, right, the proof simply turns out by saying that when we are looking into transitivity, what do we want to do? We take a word u, right, we take another word w, we want to say that there has to be some word in between, right, because we know that a shift space is irreducible if and only if it is transitive, it is the same thing. So, we want another word v coming up here in between u and v. And what does it mean by saying that A is irreducible? It means that whenever I take an I and j, there exists an n such that this is strictly positive. What does that mean? Right? That basically means that you start with a vertex I, right? You take another vertex j, there will always be a path between the vertex I to the vertex j, right, maybe of length n, right. So, this path will be n step. So, you will always get an n such that this is going to be positive, and so you will always get. So, given a word u, given a word v, given a word u, given a word w, right, you will always find a word v of length n, right, such that this is a permissible word. So, basically saying that this is a subshift of finite type is same as saying that this is irreducible, because my u could end up in the vertex, right, because this word u could perhaps end in the vertex I. Your word w is perhaps starting from the vertex j, and in between you can always find a path, that means you can find a word in between such that this word uvw, right, it is intermediating between the vertex I and the vertex j. So, these two quantities are equivalent, and hence for us to characterize or to know whether a subshift of finite type is transitive is enough, it is enough to see whether the matrix happens to be irreducible. We have a second theorem here also, and I think the proof is almost similar. So, the second theorem here says that a subshift of finite type is mixing, and when I call this mixing, it is basically strong mixing if and only if A is aperiodic. Now, this again has the same proof here, because what you are doing is you are starting with u and w, and you want to say that you can always sandwich a word of any length between u and v. So, what happens here is we know that you start with any two vertices, right, you start with any two vertices, your a n I j is always positive. Now, once your a n I j is always positive, right, what you have here is that from vertex I, right, you start with a vertex I, you go to a vertex j, right, and you can have any two vertices, there will be a word of length n. So, if your u ends at I, w starts at j, right, you have a word of length n there, but then I could also think of u starting at some other vertex, right, and then again I have a length n plus 1 and so on, and so what you get here is that this happens to be mixing if and only if it is aperiodic. There is another thing that we had seen, and in the previous lecture we had seen that if I have a shift space which is conjugate to a subshift of finite type, then that shift space is also a subshift of finite type, because an m step subshift of finite type, if you take its conjugate image, right, that will give us some kind of n step subshift of finite type depending on what is your conjugacy, because your conjugacy is always coming through a block code. But it is a very side fact, or maybe it is a very interesting fact to see that a factor of a subshift of finite type need not be a subshift of finite type. So, let us try to take an example here. So, all we want to say is that a factor of a subshift of finite type need not be a subshift of finite type. Now, we can think of this example. So, let us try to take our simple golden mean shift standard example. Now, let me define a block here, a block code here. So, let us define so this is a 2 block code basically. So, I am defining this as 0 0 is mapped to 1, 0 1 is mapped to 0 and 1 0 is mapped to 0. We have only two choices, right, it can be either 0 or it can be 1. Now, let us look into the higher block representation of the golden mean shift. So, we have seen that we can write it in terms of an H shift here. So, we have this 0, we have 0 here, right, we have so we have 0 0 here, we have 0 1 here and we have 1 0 here, and then we have now this phi, this is a 2 block thing, this also gives us a graph homomorphism, right, from this particular graph to this graph, where we are preserving the vertices and all we are doing is we are taking the images of the edges. So, this gives us 1, this gives us 0 and this gives us again back 1. So, if we try to recall this factor, right, then if we try to recall this part, then recalling this part we see that what happens here is that this also, if I take a bi-infinite walk on this particular graph, that is also going to generate a subshift. This is 0, yeah, sure. So, this bi-infinite walk on this is also going to generate a subshift, and the subshift that will be generated, since this graph is basically a factor of this graph, right. So, this is also going to generate a subshift. The subshift that is generated here will be a factor of this particular subshift, because this subshift would be given by this particular block code. So, the factor, this particular block code generates a factor, right, and this subshift is basically obtained from this subshift as a factor, and that gives us that. Now, if we try to see what is this subshift turning out to be, I have 1, I can have any number of 1s possible, but once I take up a 0, I have to again take back a 0. So, my zeros always occur in even steps, right. So, I will always have even number of zeros. So, this is basically my even shift. You have even number of zeros between any two ones. So, this is an even shift. So, what does this give me? So, this phi generates a factor, phi induces a factor from the golden mean shift to the even shift. So, the even shift can be realized as a factor of the golden mean shift. Now, we know that the golden mean shift is a subshift of finite type, whereas the even shift is not a subshift of finite type. So, a factor of a subshift of finite type need not be a subshift of finite type. Now, before we go up to something else, I would just like to correct something that I did here. Okay. So, what we are having here is we have this vertices. In fact, when we are talking of edge shifts, right, we are not interested in what we label our vertexes, we are only interested in the labeling of the edges. So, what we do here is we try to take this as, so we are calling this as A2, we call this as A2, AM plus 1, AM plus 2, right. So, we are going into the Haber-Bloch version. So, we call this as this factor and we call this as A3, A4, AM plus 2 and AM plus 3. So, we are calling the edges, right. So, this is basically our Haber-Bloch version of the edges. Now, think of this factor. So, you have such a nice construction, right, such a nice kind of computational thing coming out, say computational characterization of some kind of a dynamical system which is a subshift of finite type, but this subshift of finite type is not closed under taking factors. So, the natural question that comes up is, can we have a smallest set of all shift spaces which also contain the subshift of finite type, but they are closed under taking factors. So, we have some kind of a class of subshift of finite type and we know that this class is not closed under taking factors. So, we want to enlarge this class. Of course, if we enlarge this thing, it becomes a full shift. So, we want to enlarge this class in such a manner, we want to add some more shifts there such that that becomes closed under factors. So, this natural question was answered by, very aptly answered by B. Weiss. So, we are looking for a class, we are looking for shift spaces that contain the subshift of finite type, all subshifts of finite type such that, or which is closed under taking factors. So, if you take any factor of an element in this class, you remain in the same class. So, this was answered by B. Weiss. So, very aptly B. Weiss answered this. Say in 1973, and he defined some special kind of shifts which he called as Sophic shifts. So, he defined Sophic shifts as the elements of this particular class. Now, I just want to say something about the word Sophic here. So, if you look into the word Sophic, so this word Sophic is basically a Hebrew word, right, and this Hebrew word is for the word finite. So, there is some kind of a finite representation over here and that finiteness, that feature of finiteness is captured in this part, and that is why he called it as Sophic shifts. So, let us try to look into the definition here. So, we start with the definition here. So, a labeled graph G So, let me call it as a labeled graph as this part, this G, script G. A labeled graph G is a pair. I have a graph here and I have a function here which I call it as labeling, right, with G to be a graph. So, G is my graph with V as a vertex set and E as an edge set, and my L happens to be a function from this edge is A to the set A, which we call it as an alphabet set. So, this L is a function that assigns to each edge E in G, right, a label, say we call it as LE, right, in A. So, A gives a label. Now, what does that mean is, now that we have a graph and in the graph, right, we have basically labeled each edge. Now, look into the edge shift there. So, if we try to look into the edge shift now, right, this edge shift is going to give us some kind of a labeled sequence. So, the edge shift gives us a labeled sequence where you can define this, all your elements, your sequences are defined in terms of whatever labels are there in A. So, if you look into this factor, what we get here is this bi-infinite walk on such a labeled graph is going to give what we call it as a shift, right, on this G, and this basically will be a subset of A to the power Z. So, you start with a finite labeling. Supposing you say that here you have a finite, because your edges are finite, your labeling anyway has to be finite here. So, you start with your edges, right. For each of your edges you are basically giving some kind of a label, and for that particular label you say that okay fine, since there is a labeling here, you think of the edge shift now. So, the edge shift now can be viewed as now a sequence of labels there, right, if you are taking a bi-infinite walk on the labeled graph. So, now you have a sequence of labels, right, and you are generating a sequence of labels, and that sequence of labels is what you called as your shift here, shift coming up from the labeled shift, and that is a subset of A to the power Z. Now, think of that, if we look into this factor, if I take the shift of this labeled graph, this what shift that we generate here, right, then this is shift invariant. You see that your xg is shift invariant. There is one thing, right. So, this is shift invariant. Now, think of another factor here is that you already have this graph G, right, which is having your vertex V and your edges E, and this graph G is going to generate an edge shift, right, which we call it as xg. The graph is, this edge shift is already there with us. Now, think of this edge shift and think of this space xg. What we find here is that between E and A, right, there is some kind of a labeling. So, L is giving us a function between E and A. Now, think of that, we could think of L to be a block code, in fact a one block code, right, each edge is being labeled by A. So, we can think of L to be a one block code. So, L is a one block code and what does it generate, right? It generates a factor code, right? It generates a factor. So, let me call that factor to be L, right? It generates a factor from this xg to xg. So, what do we have here? We have xg subshift of finite type, right, and the new shift that we have here, which is basically defined using the labeled graph, happens to be a factor of this subshift of finite type. So, what we have here is that this x g is called, we call x g to be a Sophic shift, right. So, this x g is called a Sophic shift, and is a factor of a subshift of finite type. So, what is the subshift of finite type? This is x g. Now, think of that, what we have here is that we have this Sophic shift generated here by using a labeled graph. Now, a labeled graph is just a graph with a labeling. So, your graph coupled with a labeling, and that is generating another shift space which we call as a Sophic shift, and it is very easy to see that this is shift invariant. We know that all closed shift invariant spaces are subshifts, right, and since we can realize our Sophic shift as a factor of the subshift of finite type, this Sophic shift is closed. So, it is closed and invariant subset, and hence it is a subshift. So, what you get here is, by using this graph, right, you can generate something which is called a Sophic shift. Now, very interesting fact here is that when you have a Sophic shift, so first of all we note here that every subshift of finite type is a Sophic shift. Do you all agree with me? Can we say that every subshift of finite type is Sophic? Okay. We could have our labeling to be identity, is not it? Our labeling is identity, and that gives us that every vertex, every subshift of finite type, we know that there is a way of writing every subshift of finite type as a H shift, right, and then we have this identity labeling which makes it a Sophic shift. So, every subshift of finite type is a Sophic shift. The second factor is here, we have seen something else, some property of Sophic shift, but let us look into this part. A shift space is Sophic if and only if it is a factor of a subshift of finite type. We try to look into the proof of this factor. So, we know that you start with a shift space, right, your shift space is Sophic. Your shift space is Sophic, that means it is basically a shift space which is defined by a labeled graph, right. So, you have a labeled graph which defines the Sophic shift, but where is this label graph coming from, right? It is basically coming from that graph where you are labeling the edges. So, that means it is being generated by the one block code which is your label map, and that one block code is generating your is generating a factor between the subshift of finite type and the Sophic shift. So, we know that a shift space is Sophic if it is a factor of a subshift of finite type. We need to look into the converse part. Can we always say that this will be true? Think of that. If it is Sophic, we know that it is a factor of a subshift of finite type. Now, think of a factor of subshift of finite type. What is a factor of a subshift of finite type? A factor of a subshift of finite type, right, would be, again I could think of this in terms of some kind of a factor map, right. So, that is generated by some block code. Now, if necessary, we can have a higher block representation of the subshift of finite type. so that the block code that we generate becomes one step. See, all we need to define a labeling is a one block code. So, if we have some factor of a subshift of finite type, then that factor of subshift of finite type, right, can be generated using some block code. Now, if possible, we go to the higher block version of a subshift of finite type, then we can define our block code in such a manner that the block code is one step. Now, once the block code is one step, we can think of that block code as a label map, and that label map gives us a suffix shift, right. So, a space is suffix shift, then it has to be a factor of subshift of finite type. If there is some factor of subshift of finite type, it has to be suffix. So, we say that, and since we know that every subshift of finite type itself is suffix, right, basically we are getting into a bigger class which is suffix. And again this is another theorem here. A factor of suffix shift is suffix. Do you all agree with that? Why should that be true? Just take the previous theorem, right. This actually I should not write this as a theorem, I should basically write this as a corollary, because you start with that. If something is suffix, it is a factor of a subshift of finite type. So, if you take its factor, then again that will be a factor of subshift of finite type, and hence it will be suffix, right. So, a factor of a suffix shift is always suffix. So, now we have a very nice class of shifts which is closed under taking factors, right, it is closed under, and here again we can talk of some properties here. This suffix shift is a factor of subshift of finite type. We already know we can characterize the dynamical property of subshift of finite type, right, by the help of just looking at the matrix there. So, if we have an irreducible matrix, we get a subshift of finite type which is transitive, and hence we can say that our suffix shift being a factor of a subshift of finite type, it is transitive whenever the subshift of finite type is transitive, it is mixing whenever the subshift of finite type is mixing. So, you have those characterization for the suffix shift. And I think we are not getting into details, although one could start with this in various forms, but we are not getting into details here. The only thing I want to note here is that if you try to take up say any labeled graph, right. So, your labeled graph would be something like that. So, you have edges here, right. So, you have some vertices here, and for every vertex there is, right, an edge, right, joining the vertices. So, I could have something going from here to here, and it is possible to go from here back to here. This is possible. Now, if you look into this particular graph, I always have a label here. So, I am labeling here A, B, it could be A here again, B, A, right. I have A here and I have B here. So, we have just some kind of a labeling of this graph. Now, if you look into that factor, this construction is similar to the construction of finite automata. So, from the point of view of theory of computation, right, our suffix shift, it is nothing but the language of suffix shift is just the language that can be generated from a finite automata, and hence the language of a suffix shift is something which we can term regular. So, this is just some overlap with theory of computation here, but we are not going to get into details over here. And I think this is what we have for symbolic dynamics. Right? We are not, though there could be many things that we could do, but we will be using this as a tool, as an example, as a characterization sometimes henceforth in some lectures that we still have to do, but we are not getting into more deeper details over here. So, I hope this has been clear to all of you.